All right, section 8.4, wave speed. So by the end of today, I'll be able to calculate the speed of a wave traveling in a medium such as a string or air. So let's jump right in. Okay, so we've defined a few things already. We had frequency, which we said was cycles per unit time, and we had period, which was the time for one cycle. So a quick example and refresher, if you have something that is 5 hertz, okay, right here, that means it's 5 cycles per 1 second. Okay, now if you look at that, you look at the relationship between frequency and period, there's an inverse relationship there. So period would be 1 second for every 5 cycles, which means that 0.2 seconds, this would be 1 cycle. Okay, so that's the time for 1 cycle. And again, if you do the math here real quickly, 1 divided by 0.2, how many 0.2s fit inside a 1? 5 of them. Cool. Okay, so we're going to take advantage of that. In our last lesson, we talked a little bit about wave speed, and you'll notice this expression here looks very similar to our kinematic equations, a unit when we were talking about constant velocity. Okay, so velocity equals distance over time. Well, this is the exact same expression with a slight tweak. Instead of just saying distance or displacement, we're going to use the wavelength. Okay, and that's what the lambda is. And then the time is the period for one full cycle to pass by, so that gives us the unit time. Okay, now we're going to do a few tweaks on that. So I put that in a yellow box, but I would write that down. That's a handy formula to have on your formula sheet. We're going to make a few adjustments to come up with something different. Okay, so I'm going to take advantage that t is equal to 1 over frequency. So if you notice, I've replaced the t on the bottom of that expression with 1 over frequency, and by the time you do your division by a fraction, you bring that f up, you come up with something that says v equals frequency times wavelength. And this is what we call our universal wave equation. Okay, so please note that, write that down. That's one of the big ones you need to know. Let's just extend this down. If you looked at this from a unit perspective, velocity is measured in meters per second, frequency is cycles per second, and lambda, or wavelength, is meters per cycle. Now we've already talked a lot about canceling units, so if you set this up and you notice cycle and cycle cancels, what are you left with? You're left with meters per second. Okay, so this checks out from a unit analysis. And again, just a reminder, you have some marker point here, that's the blue line. As this wave travels past, you know the length of the wave, and if you know the period, which is the time for one wave to travel through that blue line, you can come up with the velocity of the wave. So let's actually do some calculations here in practice. I'm just going to grab my trusty calculator because I've had some seriously funny boo-boos in the last few videos, so let's try and avoid those. So let's start with a harp string supports a wave with a wavelength of 2.3 meters and a frequency of 220 hertz. So we're just going to start off with some real basic stuff. Okay, making sure we can put everything in the correct location and that everything has the right units. Frequency is in hertz, lambdas in meters, those both check out, that's what I want. So V equals 220 times 2.3. And again, I'm going to trust my calculator because of my last funny boo-boo on the last video, which I've since edited away. So we have a wave speed of 506 meters per second. Okay, and we're going to talk a little bit about guitars and sound and waves and strings versus air shortly, but that's just how the calculation works. Okay, so a trumpet produces a sound wave that is observed, not that you can see it, but is observed traveling at 350 meters per second with a frequency of 1046.5 hertz. Calculate the wavelength of the sound wave. So again, we're going back to our universal wave equation. Okay, this time though, they've given us the velocity, they've given us the frequency, make sure I write it down correctly, and we are solving for lambda. Make sure I get the right symbol in there. Solving for lambda. Now I'm going to divide both sides by 1046. And we'll come up with our lambda in meters. So let's say 350 divided by 1046.5. and I get 0.334 meters is the wavelength, which is the same as 33.4 centimeters. Okay, so just slightly larger than a ruler. Okay, your standard classroom ruler. Okay, that would be the full cycle from here to here of that wave. Okay, there's a couple here to try if you want to pause them. Again, it's just the same 3-variable equation, so I'll pause it here for a second and then I'll just erase the answers for you. Okay, so let's just have a quick look. If a wave has a frequency of 230 hertz and a wavelength of 2.3 meters, we should come up with a wave speed of 530. So you're just multiplying those two numbers together. If a wave has a speed of 1,500 meters per second and a frequency of 11 hertz, what is its wavelength? So you'll be dividing those two numbers. You should come up with about 140 meters. And again, remember the textbook answers are rounded off, so don't panic if it's not exact. If a wave has a speed of 405 meters per second and a wavelength of 2 meters, what is its frequency? This would be a division case. Okay, now they've expressed it in scientific notation. Don't panic. Okay, that's the same as 200 hertz. And again, they've done some rounding off, so don't panic if it's your answer is slightly off. Okay, this is just a little tidbit of information that's kind of important to know. Factors that affect wave speed, we've already talked about. The medium is important, so if things have strong intermolecular forces, so solids in particular, liquids can be very tight together in the same way, they tend to transmit energy more effectively, more efficiently, and you get faster wave speeds, longer distances they can travel, those types of things. If we're looking at gases, and this is just an interesting little note because, and I always get this backwards, which is why I want to put this in here, because it's, for me, it's one thing I always forget. My logic says, well, if solids travel faster and are more efficient, then a cooler gas would be denser, so it should be more efficient than a hotter gas. And it's actually backwards, okay, which is why I wanted to put this in here. So an increase in temperature, because the molecules of the gas are moving faster, they actually transfer their kinetic energy more efficiently. So make a little note of that. It's not a huge thing, but it's one of those ideas that's counterintuitive. You would think a denser gas would be faster or more efficient, but it's actually the opposite. Okay, so just make a little note of that, please. Okay, now linear density and tension. This is a section that tends to give people some confusion. We'll look at a guitar string, and if we have time, we'll look at some other demos. But linear density is the mass per unit distance. Okay, so something like this, we use the mu again, which is the same as friction. Don't panic, we can use those letters in different locations. So this would be written in kilograms per meter. Okay, and usually it's small for something like a guitar string, but the units on this are kilograms per meter. Okay, and that's a type of density. So when you see guitar strings, you'll notice there's a thick string and there's a really thin string. Okay, and they all have different sounds. Okay, the next part is tension. The tension of the string makes a big deal. Okay, so I'm not going to prove this. If you want to go to the PDF and find that proof on Wikipedia, you're welcome to look at it. Good luck. So we're going to take this one as just being correct the way it is, but you'll notice that velocity is equal to the square root of the tension force in the string, okay, divided by the linear density. Okay, so on a guitar, you'll notice we have thick strings down here, we have thin strings down here. Okay, so they have linear densities. We use the pegs at the top of the guitar to change the tension, and I'll try and show that to you in a second here. I'll make a quick little video to highlight that if you haven't seen that done. But I do want to highlight one key piece here. There is a string wave speed, and there is an air wave speed. Okay, and they are not the same thing. So when you pluck a guitar string, this guitar string here will vibrate, okay, and there will be a certain frequency. Now that frequency will give a certain wave speed on that particular string. Okay, what you hear though, the frequency disturbs the air particles via the string and via the sound box, which is the big hollow piece on the guitar. It disturbs the air particles with the same frequency as the vibrating string, but because they're in two different mediums, they have two different speeds. Okay, that's really important to take a look at. So when we go through some examples, you might get some really, really big or fast wave speeds for solid objects like strings and things. But when we start to talk about the speed of sound in air, you're going to see that they should be around 300 and something, 330-ish. Okay, and we'll do more about that in the next lesson. So please distinguish. There is a string wave speed and there is an air wave speed. What they have in common is frequency. Okay, but because they are acting in different mediums, one's a gas, one's a solid, their actual speed, their wave speeds are very, very different.
Okay, so this is a guitar. It's normally a 6-string, but I'm missing my low string here, right here. I broke it a moment ago, so yay for me. So you'll notice they have different thicknesses, which means they have different linear densities. They all sound different because of that linear density. Okay, and then the other part that helps control the sound, okay, is the tension in the string. So I can turn the tuning pegs here. So if I flick the low string here, see if I can make it a little louder. Okay, so you can hear how that changes. And the key piece you want to take away from this, though, is that both the linear density and the tension affect the velocity of the wave. And why that's important is from the universal wave equation, V equals frequency times lambda. If you change the velocity, then you also change the frequency and the wavelength. And what we hear is the frequency. Okay, you don't see the wavelength, you don't see the wave speed, but you do hear the frequency. So whenever you change the linear density, the tension, that affects the velocity, which affects the frequency. And that's what makes the sound in your ear sound different.
Okay, so let's have a quick look and I'll show you where people have most of their problems. On our class wave machine, I'll try and show you what that looks like in a minute. Maybe I can pop down and look something like this. Okay, so you have a mass hanging going over a pulley. The mass creates tension in this string, and then when you pluck the string, it will vibrate and send a wave back and forth down there. So you can control the tension of the string by adding more masses. You can calculate the linear density by measuring the length of the string, putting it on a scale, okay, and dividing the two out, and then you can see different, you'll hear different values. So if I get a chance, I will try and show that. I don't know if I'll be able to film it. It's very quiet, so it's hard to show. So here's what we have. On your class wave machine, you have a string of mass 350 grams and length 2.3 meters. Okay, so first things first, that guy makes me nervous, okay, because it's in grams. Okay, you would like to send a wave along the string at 50 meters per second. What must the tension of the string be? Okay, so you'll notice they've converted it to kilograms, which is awesome. What must the tension in the string be, or the string be? So we're looking for F of t. So if we start with that, I would probably do a little bit of algebra work before I started trying to put numbers into this. So if I want to solve for F of t, I need it by itself. So what I would do is I would square both sides. So if I squared both sides, that squaring undoes my square root. So I'm left with V squared equals the tension force over the linear density. Then I would rearrange linear density times velocity squared would be my tension force. Okay, so now I just have to input the information I do have. I know wave speed, which is 50. I know that I have a linear or a mass of 0.35 kilograms and a length of 2.3 meters. So if I take that, my Linear density would be 0.350 divided by the 2.3 meters. So there's my density. My velocity is 50 all squared, and that should give me f of t. Okay, and I'm going to go slowly here so I don't punch in a ridiculous number, and I'm going to trust my calculator to help me along the way here, and I get 380 not meters per second, I almost blew it, that's pretty close. 380 newtons is my tension force. Okay, so there's a couple to try. So these are some practice questions. So if you want to pause it and then try them, I'll try and go through them really quickly. Okay, so let's take a look. If a 2.5 meter long string on the same wave machine has a tension of 240 newtons and the wave speed is 300 meters per second, what is the mass of the string? Okay, so we know a couple things. I'm going to do number one first. So we need mass over length. We're looking for m. That's our goal. We have an f of t. We have a v. Okay, so if we go back and look at for our formulas here, v equals the square root of ft over the linear density. So v equals square root ft over mu. Okay, so I know a couple of these things. I know this one, and I'm going to try and work with this piece down on the bottom. So let's put in what we know. Oh, let's rearrange it first. Let's go v squared equals ft mu, and then I'm going to rearrange because I know tension, because I know velocity, and then I can replace with mu, I can replace that with mass over length. Better give myself a little bit more room here. And then the mass is going to equal the tension force times the length divided by velocity squared. So let's see what happens here if I can remember the numbers. The tension force was 240. I'm going to times that by the length, which was 2.5. And we're going to divide that by 300 squared, and I should get this really small number. Okay, and that would be measured in kilograms per meter. And I'm going to warn you right now, I ask for units. Oh, sorry, not kilograms per meter, just kilograms. Pardon me. I can get rid of that. I ask for units in my questions to make sure you have the understanding of what you're working with. Okay, so I'm going to guess they probably will write their answer as 6.7 times 10 to the negative 3 kilograms. So let's go take a look. 6.7 times 10 to the negative 3. Okay, so that's how you manipulate those equations. I'll leave the next two for you just for the interest of time. Just note a couple things here. This is your mu. Okay, this is your V, and what tension is required. Maybe we'll do that one real fast. If I can clear it out fast enough, I can. Awesome. Okay, so V equals square root ft mu. So this is number 2. And then we should have the square root of, oops, sorry, I'm going backwards. We want the tension force here. And we want 0.2. I have the correct units. I'm going to get rid of my V because I know it. It is 200. Okay, so again, before I can touch that F of t, that tension force, I have to deal with the square root. So I'm going to square both sides. And I end up with, whoa, that's a strange 200. I end up with 200 squared equals ft over 0.2. 200 squared times 0.2 is ft. Let's see if I can get this one right. Times 0.2, 8,000. So I should have 8,000 newtons equals ft. Let's see how well we did. 8 times 10 to the 10 to the third, so that's the same as 8,000. Okay, and then lastly, if a string on a wave machine has a linear density, so again we have a linear density listed here. We'll do number 3, we'll do it in blue. So we have linear density, and we have force. What is the wave speed? So let's do that really quick. Ft over mu. And because we have everything on the right hand side, this should be fairly straightforward to come up with V. So 250 divided by 0.011, and then take the square root, and velocity should be 151 meters per second, and they have 1.5 times 10 to the 2, same diff. Okay, so section 8.4, 1, 2, 3, 4 would be good questions. Sorry, 1, 2, 3, 4, 5, 6 would be good questions. This is one of my favorite areas, is earthquakes. You get P waves and S waves. They are both longitudinal waves, and S is shear waves. So this is longitudinal, S is shear or transverse waves. And what's really fascinating, and I would normally digress and talk about this for quite a while in class, shear waves can't go through water, for example, because they need molecular connections in the substance. So shear waves is what pushes the ground up and creates large little cliffs and things to rupture the ground in an earthquake. A P wave can actually travel all the way across the earth because it's a compression wave and it's in the longitudinal direction. You can actually feel it or measure it on the other side of the earth. So when it hits like a liquid, like lakes and things, or magma, P waves can go through it, where shear waves or S waves cannot. Just a little side note for earthquakes. Thanks for tuning in.